This is what I made. A demo video that nobody wants to watch.
I'm going to talk about something very interesting, but
yeah, I guess by the time he gets to the but part, nobody is interested in his interesting story. So this is after my AI application removes all the silences and pauses.
I'm going to talk about something very interesting, but
okay, that seems more interesting, and people might stick around to learn more about these things that he wants to talk about. Welcome to Let's Build AI, where I'll be building cool AI applications which you can actually use yourself to do a lot of tasks that you do daily automatically. And for lesson 0, I thought about what I should make. And I said, why not make something that helps me edit this video that you're watching right now? So I searched for some video editor that would remove silence from videos. I did my own research. I found this article here, lists a bunch of software that does automatically silence detection and silence removal. So let's see here. So this one is an add-on that you have to install on Filmora, remove silence from video. The feature has to be purchased, so not only you have to buy Filmora. How much is Filmora? It's $49.99 annually. Okay. And you have to buy this one on top of that just to remove the silence. Okay, that's a red flag here. Because in these series, we want to make everything from scratch using AI. And also, everything is open source and free. So the code would be in my GitHub. Also, it removes silence using 3 major parameters: the threshold, the buffer, and the duration, which is, okay, so you have to set the duration of the silence, the minimum duration, some threshold and stuff like that. I want AI to automatically define silence without any hyperparameters here. Let's see what other option we have, because we shouldn't give up. Maybe there's something. Oh, Adobe Premiere Pro. I'm sure this is good. Let's see how much it costs. Premiere Pro plan is $21 per month. Okay, that's worth removing some silence here and there. All right, seems like we have to start building it ourselves. Now, this is what I made. A demo video that nobody wants to watch.
I'm going to talk about something very interesting, but
yeah, I guess by the time he gets to the but part, nobody is interested in his interesting story. So this is after my AI application removes all the silences and pauses.
I'm going to talk about something very interesting, but
okay, that seems more interesting, and people might stick around to learn more about these things that he wants to talk about. So first off, how do we get from this guy to the guy below? Let's use Python, of course, for deep learning material. And I'm going to use this library called Transformers from huggingface.co. And they have a lot of good pre-trained models, so we don't have to train them from scratch. So I will use the auto tokenizer feature, because the goal is to kind of make a transcription of whatever I'm saying, and at the same time get the timestamp of when I'm speaking, when I'm not speaking gibberish, of course, and only include those and discard every part where there's silence. So I'm gonna need the auto tokenizer and also auto processor, and also auto model for CTC, which is connectionist temporal classification. And this auto model for CTC, this CTC method has been around forever, for like ages, and it's nothing new, nothing revolutionary about this thing. I will also would need to do some PyTorch, some basic PyTorch operations. So I'll import torch. What else do we need? We probably will need some NumPy as well. I should have probably imported everything all at once. So let's do it. I'm probably gonna write some files from the system. So let's import path from pathlib. Import path. What else do we need? Because we're going to edit the videos that we record directly in Jupyter Notebook, or I can give you an actual Python script that you can run and remove all the silences. So let's import MoviePy, and I don't need just everything in MoviePy. So from MoviePy, I will need only the editor part. So the editor, well, I'll need a bunch of them. So I'll just import the editor. From MoviePy, import editor. Perfect. Since we're dealing with sound, it's useful to use the Librosa package. You'll see why later. And also, since I don't want to clutter my SD drive, so I'm gonna create a cache directory that will kind of point to a hard drive that I have. And this is the path for that. Let me copy paste it real quick. Okay, as NP. Let's go. Now, we already have a pre-trained model, so we don't need to do much. We just need to instantiate the model using the auto model for CTC, and I'm gonna use a from pre-trained method from Hugging Face. And if you scroll into the wave to wave 2 vector documentation, you'll see that there's an example for object character recognition, and they're using this pre-trained model. So let me call this my model ID. I'll just copy. So my model ID, which is the path on the Hugging Face for a pre-trained model, I'll use it to download that. But at the same time, I don't want it to clutter my SSD, so I'll put the cache directory as cache directory here. I'm also gonna create the processor, and this processor helps us do the tokenization, so turn all of the tokens into actual characters, and helps us with some post-processing. So I'm gonna use the auto processor that I just imported from pre-trained and model ID, the same argument. And potentially, if it also downloads some extra files, I want to put it in my hard disk. So it should be fine. So let's have it load all the data that we need. It will download it from the internet for the first time, and then it's going to load it into my memory. By the way, I'm not going to use any GPU, so it's going to work on Mac, Linux, Windows. You'll be good to go. You don't need to have GPUs for this one because we're just doing inference. We're not going to do any fine-tuning or model training. So until it downloads, let's go to the next step, because the next step is to get an actual audio sample. But why not go straight into videos? Because we are, at the end of the day, we are going to edit videos. So I will need a video file, and I'll use the editor that I just imported, and it has this video file clip inside. So let's call it video file clip. That would just take the path of a video that you have. This is in my current working directory, the same directory that the notebook is. Let's import demo.mkv. It works with Matroska as well as MP4 and other formats. So demo.mkv. Demo.mkv. Please load that. Now, this model that I'm importing, it's taken a while because my system is kind of occupied right now. The model expects an audio file to be turned into a NumPy array. So from this video, I need to extract the sound part. And it is pretty simple. I'll create a variable called audio. And on the video, I will call the audio to get the audio segment of the video. And also, I need to call to sound array, so that it will give me not the audio file, but the actual NumPy array. So the video that I actually imported is this video.
I'm going to talk about...
As you can see, it is 18 seconds. Okay, our model is loaded now, so we can get the audio part. And also let's have a look at the audio part. This is a NumPy array of type float. If you look at the shape, you'll see it has 800,000 plus samples on 2 channels because it's a stereo file. Well, there are some caveats here. The model was pre-trained using mono channels, so we need just 1 channel for this one. We cannot work with 2. And Also, the model has been pre-trained on sample rate of 16,000, 16K. So we have to take care of these two parts. The first part is kind of easy. We can actually just work with one of these channels. Because I'm not doing a Dolby IMAX movie type of thing that each channel has like different sorts of information and speakers. So all I need to do is just to overwrite audio and say, I just want the audio that has all the samples from the first part, just the first channel, and we should be good to go. Now, if you look at the shape, it gets rid of the second channel. Now, it's good to always be able to listen to the audio to see what's going on. So initially, I imported from IPython the display function as D. So I'm going to use D, which has an audio function and also video function. So you can display audio or video. It can help you read a bunch of files from your disk or this NumPy array that we have here. So I'm going to say, please read audio. And I'll also need the sample rate. So let's set the rate to the actual rate that it is, which I believe is 48,000. Let's check. If it sounds like I soloed helium or the pitch is really low or high, it means that we kind of messed up. Right off the bat, this seems like it's 16 seconds, so it might not be the actual sample rate.
I'm going to talk about
something
very interesting.
Okay, so the sample rate, therefore, I believe is 41,000. Let's try this one out. It's 19 seconds now.
I'm going to talk about
Oh, so it's something in between.
something very interesting.
Well, that's interesting. Because to sound array, if you look at the documentation, it says this FPS is actually the sample rate. And it says for optimal quality, use 44,100. Okay, all right. Now this is what we should be working with. So when you call this function, video, audio to sound array, it's going to use a sample rate of 44,100, regardless of what the original sample rate is. Now we get 18 seconds. Let's hear it.
I'm going to talk about
Okay, that's me. I kind of recognize my own voice and pitch. So now we can visualize the sound. We can check it at any time that we want. Let's resample because initially I said this model expects it to be 16,000, the sample rate. That's why we imported Librosa, because right now I'm going to call Mr. Librosa and say, please resample. And it takes your NumPy array of the audio file, original sample rate, and the target sample rate. So the NumPy array is called audio, of course, the one that we worked with. Original sample rate was 44,100, and target sample rate is, we want 16,000 because our model expects this. Now, if you look at the shape of sound, it goes from 810,000 to 294,000. We're downsampling it. So for 1 second of audio, this takes 44,100 samples. But for this one, for 1 second of audio, it takes 16,000 samples, which is far less. But if we did the resampling correctly, the audio should sound the same. The quality might be degraded, but it should sound actually the same. So if we set the rate to 16,000 now, hopefully, we get 18 seconds, and does it sound the same?
I'm going to talk about
Exactly, perfect. Now it's kind of ready to be input to the model. The problem is, right now sound is a NumPy array, so we have to turn it into PyTorch tensor. So I'm going to use the processor that we imported and give it the sound file to turn it into PyTorch tensors. Because Hugging Face works with TensorFlow and PyTorch, you have to specify what kind of tensors you need here. So I will say return tensors type PyTorch. And also it's cool to set the sampling rate. It's safe. Of course, if you don't set it and the sampling rate is different, you're gonna get terrible results. So let's put 16,000. If you input anything else, it will give you an error. So this is gonna give me a dictionary of input values. So I'll just ask for the input values. I don't need a dictionary. Now I can store this into the inputs. Now let's have a look at the shape of the inputs. It'll potentially add a batch dimension here, but it'll maintain all the data that we had in a NumPy array. Now let's use the model that we imported. Model, let's put it into the eval mode just to be safe. We don't update any weights. And let's disable gradients. So that's why we imported Torch. Torch, no grad. Context manager disables calculating gradient, so it doesn't register the gradients in the forward propagation that we're gonna do. So I'm gonna get the logits from the model. So I will call model on the inputs and get the logits from it. Okay, that was pretty quick. Now the logits are of this shape. The batch size, 9, 18, and 32. Okay, so what do these mean? Because we went from a tensor of size 294,000 and something to one that has one batch, mini batch. So nothing changed here. But this part, 918, is the actual downsample sequence from this value into 918. And these 32 values are the logits, or let's say the pseudo probabilities for each sample being a certain character. So my 18-second audio now is 918 sequences of sound, and each sequence has an associated probability for a different character. From A to Z, all the way to unknown, and padding, start of sentence, end of sentence. We can actually have a look at the different characters that are available using the processor. It has a tokenizer, and we can get the vocabulary for that. And you can see these 32 different values. So value 0 is pad, 1 is start of sentence, end of sentence, 3 is unknown, 4 pipe, which probably means silent, and the rest are the different Latin or English letters, and 27 is apostrophe. So that's good, that's amazing. Now this is kind of problematic because I want to know in this 18-second audio file where each one of these letters start and end. I no longer have this actual length of my audio file. I just have 918 sequences. So there's a nifty function in the processor that's called processor decode. And what it does, it takes the logits as NumPy array. So we have to turn these tensors into NumPy array. And also has this option of output word offsets. So let's give it the logits. Remove the batch dimension because we only have one. Turn it into NumPy array. So NumPy, and please return word offsets equals true. Let me store it into an output variable. So let's have a look at the output. Okay, now we get the text part. I'm going to talk about something. We get the dictionary that has word, which is 2, start offset, and end offset. So we probably now have the actual offsets, which we can use to calculate the start time and the end time for every word that is being uttered. So these start offset and end offset are in the same unit as this 918. So it says I'm starts from the sequence 77 up to 82 in this unit, which is kind of gibberish, nonsense. We don't understand it because it's not seconds, it's not minutes. So we have to find a mapping from these offsets to the actual seconds or the actual samples that we worked with. But if you notice, the original audio size had this amount of samples. So if I divide this by the final sequence length, I'll get 320 and something. I'll only need the integer value, so it's 320. So it goes from the sample rate down to 320 times smaller. This 77 actually means 77 times 320 in our original array. 82 means 82 times 320 in our original array. Now, if we want to get it back into seconds, we can invert it. So this number 320, if I divide it by my sampling rate, I can actually get the actual seconds value. So divided by 16,000, which was the sample rate, I'll get this value, which is 2% of 77 is where word I'm starts. 2% of 82 is where I'm ends, and so on and so forth. So if I go into this output and ask for the word offsets, I can make a list comprehension that would say for offset in get offset. Let's see what we get initially. Output word offsets, but I don't want the actual offset. I want the word submodule, the word index. That's the word. And also, what was the other one? Start offset and end offset. So let's recreate this dictionary using a second dictionary. So the second dictionary, I need offset word. I need the offset start offset times the 0.02, which will actually give me the second value, the second in terms of time. We can also multiply by 320 that we got to get the actual sample with 16,000 sample rate. But it's more intuitive to work with seconds. So start offset, offset, end offset times 02. So now I no longer need the dictionary. I no longer even need the word part because I need just the offset start and offset end. So let me put it in a list. We should be good to go. So this is the start of the first word and the end of the first word. So let me assign it to a variable called timestamps. Timestamps. So timestamps, have a look at it. It has the start and the end of every word that has been uttered in that video. Okay, so anything outside this range of timestamps is silence. So we can remove it. So let's try doing that. But before we do that, we have to be mindful of one problem that might arise, which is if the first timestamp is 1 second and 54 cents to 1.64 seconds, and the second one starts before this one, we're going to have overlap and it's going to be counted twice. So we want only the parts that are not overlapping, and the parts that are overlapping, I just want the union of them. So I searched the internet for a function that takes a series of numbers and creates the union for them. And I found the actual function that does that. So I put it in this union. And by the way, this function needs this thing called interval, which I'll need to import from SymPy. So import from SymPy, import interval and union. It does some basic mathematical operations for us and we should be good to go. So now let's call this union function that we created on our timestamps, and hopefully it gets rid of any overlap in intervals. So now let's store it into intervals. Now I need a new audio file that only includes the original audio but within these intervals which I spoke. The rest should be silent and removed. So new audio, I'll start with a list. Write a for loop in a lazy way. You probably can use NumPy to index into these intervals. But let's write a for loop for interval in intervals, which is each one of these. The start is interval. It has a start property, so I can get the start. And the end, of course, is the interval's end property. Now, since I have loaded my video into this video object here, I can use MoviePy's subclip to make small clips of these intervals and add them to this new audio. Let's actually call it new video because we're not doing separate audio video processing. We're doing it in one bit. So new video would add, call append on it. It would add the original video's subclip. And if you look at MoviePy's documentation, it says time start, time end, and it is in seconds. So I can actually give the start and the end here. Start, end, and it'll actually give me the video's subclip that I spoke. Now, if I run this for loop and look at the new video variable, I will end up with 1, 2, 3, 4, 5, 6, 7, 8, 9 subclips that are in order of these intervals. So I can easily call the editor's concatenate. Since we're concatenating video clips, that's easier to call the concatenate video clips. It'll get a list of clips you change them together in the same order, and you can add a bunch of other stuff if you want, some padding, some transition between different clips. We want it to be seamless. But if you want transition in between every part that you trimmed, you can add that too. You have the functionality to do so. So let's call it on our new video list, and we'll get our final video, which is in this object. Now, if I want to save this one to the disk, I can easily call final video, write video file, and it uses FFmpeg, which is really robust, has a lot of functionalities, and you can actually give it the file name in the current working directory, test fixed, let's call it that, .mp4. Okay, after it's finished writing to the disk, we can call it the video, display the video here, and the name is this one, test fixed, the one that we just wrote. It might be too big for this display, so I will change the width to 1080 by height of 728. Okay, so this is the video now.
I'm going to talk about something very interesting, but
okay, it doesn't sound right because we only took the parts that I actually spoke, which are really short periods of time. So like this is probably like 100 milliseconds. This is like 200 milliseconds. So one thing we can add to our code to fix this error is some padding between the intervals that's gonna be cut. So here in my for loop, when I say, please take the start of when I talk and the end of when I talk, and take a sub clip of that from the original video and create a new segment in my video, I can set a pad argument and set it to, let's say, 1 second, just for illustration purposes. Then from the start, remove amount of pad, which is 1 second. So go back, and at the end, add the pad. So it kind of expands this 1.54 to 0.54, and the end from 1.64 to 2.64. We can actually, because we might end up with overlaps, we can actually use this padding way before when we actually get our timestamps. So we can set the pad here and say offset, which is the beginning, minus the pad, and the end, and put them next to each other, plus the pad. Now if I run this, I'll get the, instead of 154, I'll get 0.54. Instead of 164, I get 2.64. Now when I call the union on the intervals, it's gonna get rid of all the overlaps. So let's run it again. Now we added 1 second padding, 1 second breathing room into our chaotic clip now, which is...
I'm going to talk about something very interesting, but...
Now anyone who listens to this might get a heart attack, a panic attack. So let's play around with 1 second padding here. So added a pad of 1 second. Now we end up with 3 segments. Concatenate them and write them to disk. Now let's watch.
Something very interesting.
So we can see it got rid of the longer pauses and made it more laid back and relaxed. So if you're doing that type of content, it might be useful for you. The actual value that I set in the demo that I showed in the beginning was 0.3 or 300 milliseconds of padding before and after each word, which gives you something like this again.
I'm going to talk about something very interesting, but...
So it is very fluent. There's no choppy, just hectic cuts, and it's not as lax as the 1 second pad. So I guess 0.3 is the sweet spot. You can play around with it, but that's pretty much the whole pipeline that we need. And we actually turned our really lengthy, with a lot of pause video into something more reasonable. So we automatically use AI to cut and fix the video itself without using any of these paid software. I hope you enjoyed this video. There's a lot of room for improvement here. We can fine-tune the model to identify any filler words that if you use or someone who are you're editing for uses, like these filler words. identify them and also remove them as well. So that would be the next step. In the next video, we're gonna fine-tune an actual model. And this is why I like the AI approach, building from scratch using open source, because at the end of the day, we have so much flexibility. Whereas with software, not only we have to pay, but you have little to no flexibility when it comes to editing the video, or either you have to do it manually or you have to stick with this algorithm that was written. And it's not usually as robust as the actual automatic speech recognition that we had here to identify the words that we spoke. So in the next one, we will also make a deep learning model that can turn low quality audio into high quality audio. It is really helpful for those of you who don't have high quality microphone, so you can increase, enhance, do some sort of super resolution that's done on images, but actually on audio. That would be interesting to do. So please like this video to help the video go up in the algorithm and for more people to see it. The only reason I'm doing this series of Let's Build AI is because I want to help others understand AI in the new age of AI, learn how AI works, use it to solve everyday problems, help them, and use it for good to facilitate their lives. So I appreciate if you subscribe to this channel, hit the bell notification icon so when I post the next video, you'll be notified. But also share it with your friends, family, colleague, because the more this video gets out, the more people see it, the more motivated I'll be to make new ones, because I will know that people are actually watching these things and these are actually helpful. If not, there's no reason for me to make these things. Thank you so much and see you in the next one.